I'm an idiot. Yeah, so one way to do this lab is to grab your iOLab, turn it on. There's a little microphone. You could take a ruler, meter stick at 20, take it at 20, and then by yourself, and as I just said, this is out of view, but that's because my computer's up high. I'm actually on the tabletop. I have my iOLab sitting right next to my ruler. I'm going to drop it from 20, but I'm going to do something a little bit special. Right before I drop it, I'm going to say drop. Okay, so watch. Drop. Now here's the hard part. If you were watching closely, I let it go right when I said drop and right when it hit the ground. So this is right where I started to say drop, and highlighting to the first spike is where it hit the ground. And technically I could zoom in on this so that I get a good, no, zoom in, so that I get a good window. Now, if you do this, it will give you the change of time. I would prefer that you do it this way because the 20, the 30, or the 40, the 60 distances are going to be very hard to do with a stopwatch unless you have a really good way of doing it. What will be a pain is you're going to have to do this 3 times for 8 different distances. But all you would do, if you do this way, start from where you said down or drop or snap your finger as you let it go or whatever you need to do. Start it there, and right when it hits the ground, you can freeze it, okay? Write that time down as time 1, okay? One thing I'll caution you is don't try to do 3 on the same thing. I would pause it every time. Trial 2. I didn't say drop. Drop. So I have trial 2. I can zoom. Why don't you zoom? In trial 2, I start from the end. I catch right there. I get 0.267. And then I probably didn't have it at the exact right distance, which makes sure that your eye is level with the mark on the thing. So write down 0.2667 for your second time for 20 centimeters. And then the last time, drop. Wow. Let me try that again. Drop. Why is that? Let me go back and look if this is just, wow. I guess my voice is jumping around. Yeah, this becomes a real pain. So let me try that one more time. Drop. So if I zoom in and then go to this, and I get 0.2. My times are really far off because I'm dropping them from different heights. Your times early on for the very small distances are going to be kind of bad. Always in this lab. For the short distances, the times are kind of iffy. They get better and closer together for the final heights, just because it's falling longer. You tend to make less errors starting and stopping. But so use the microphone, do something like drop or snap your fingers and let it go. Set the iOLab right where it's going to hit the ground so that it'll pick it up with the microphone. And then take the time from the first thing where you said drop or you snapped your finger to right when the spike begins from hitting the ground. It's one way to measure this. As I said, you could also have an assistant with you with your phone or with your like a stopwatch if you have an actual stopwatch. It is really hard to get the timing right for the first couple distances. It's just not in the air that long. You're basically hitting start and then stop right away. But you'll get better. You'll have more time later on. as the distances get better. Okay, now on the iOLab, if you use the iOLab for the microphone, record blah, 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 blah. If I look at this and I highlight this, notice that this delta t, it's giving me to the 1 times 10 to the 5th is the smallest digit. So my uncertainty in time is half that. It would be 0.000005 seconds. If your phone, my phone, if I start my stopwatch, if I start it and stop it, my phone goes to hundredths of a second. So the uncertainty of this measurement would be, well, the resolution would be 0.01 seconds, and the uncertainty would be 0.005 seconds, okay? That's your delta t here. That's the only time you're gonna need this delta d and this delta t. We're gonna do a different style of error analysis. But essentially, if you can come up with another way to measure the time, do it. But I want the time it takes for them to fall, and I want you to do 3 trials. The reason we're doing 3 trials is we're gonna average them, and hopefully that will get rid of a lot of our error. It'll get rid of our random error, and I'll talk about that later. So you're gonna do 3 trials at each distance, 20, 40, 60, 80, 90, 100, 110, 120 centimeters. Okay. Then, for the data analysis, only for this first one, but you need to do it for all of them. It says 10 centimeters. That should be 20 centimeters. Really, for everyone here, it's just for one of them. For one of the distances, I want you to show me how you do this. I actually changed this lab, and it originally had 10 centimeters, and 10 centimeters is way too fast with any of these methods. And I'm sorry, I just left that typo in there. So we need to find the mean free fall time. Mean time is just average. You add these 3 times together, divide by 3. That's really super easy. It's shown here as a summation, but all it means is add T1, T2, and T3 and divide by 3. You're gonna write that on the table of results here for each one. So you're gonna need to do it for each one, but you only need to show it. So copy this and repaste it underneath and actually put the numbers in to show me the 20 centimeter time or whatever you use. Next, I want the mean free fall time percent uncertainty. How you do that, how Excel does it, is if you have multiple values for a given trial, you take that average, that mean time that you divided by 3. You take T1 and you subtract it from the average, or you take the average and you subtract T1. Doesn't matter because you're going to square it. So you take the difference between the average value and the actual value of T1, the average value and the actual value of T2, the average value and the actual value of T3. You square them and you sum them all together. This is a little weird, but essentially, you then need to divide it by the number of trials minus 1. If you take a stats class, we'll get into why that is. For very, very big amounts of, let's say we had 1,000 data points, this wouldn't matter. You could just put n. We're going to use n minus 1 here. N is 3. So this is really sum or square these, sum them, divide by 2, and then take the square root of that. Divide that whole thing by T average. Another way to do this is you could actually take T1 minus T average, dividing the whole thing in here by T average, because if you put this inside the square root, it would be T average squared, which would mean it could just be the denominator under this. But either way you want to do it. Show that for the 10 centimeter, but you're going to need to do that for the 20 centimeter. You're going to need to do that for each of the distances. I want that here. We're going to actually look at this in the questions, so make sure that you do it correctly for each of them. The next thing we ask you for is, once you've done all this and you've got these average times, I want you to make a graph in Excel of average time, and so make a column of distance and make a column of average time. You're going to have something that looks like this right here, these two columns. You need to graph distance versus average or mean time. When you do that, make sure the distance is on the Y, mean time is on the X. And you're going to put in a quadratic trend line. That quadratic trend line is essentially going to graph it as this, but with what it's really going to graph is, where did I show that? It's really going to graph this equation right here, okay? And we'll come back to that in a second. So make an Excel graph, graph distance versus time, put a quadratic trend line on. Remember, on your graphs, they have to have a title. They have to have axes labeled with units. So on the Y, it will say distance, centimeters. On the X, it will say time, seconds. You're going to put a quadratic trend line, make sure the trend line shows on your graph, make sure the R squared is on your graph. And then when you do that, make sure that you do not have the Y intercept be 0. Do not set y-intercept to 0, okay? Leave it. We're going to talk about that in a minute. So you're going to get this trend line that looks like AT squared plus BT plus C. That's what your equation will look like for a quadratic trend line. We know this is our equation for free fall. So you can look and you can compare these and you can see that A, whatever your A coefficient is, it is identical to G over 2. So if I multiply whatever my A coefficient is in my trend line by A, or my A coefficient by 2, I get my experimental value for G. However, I'm in centimeters versus seconds. G in centimeters per second squared is 981. I put this in meters. If I want to turn this into centimeter per second squared, I would multiply it by 100 centimeters over 1 meter. So G theoretical is 981 centimeters per second squared. I should have put that there. You should all know that. They've got to match, or you can turn your coefficient into centimeters, or you could actually put your distances into Excel as meters. I don't really care what you do. But they, theoretical and experimental, will have to have the same. So experimental G comes from the A coefficient times 2, the A coefficient, the coefficient on the T squared or X squared of your trend line times 2. The theoretical is 9.8 meters per second squared. I want you to take the theoretical minus experimental over theoretical times 100%. That is known as the percent error between the theoretical and the experimental. And now, all this stuff on here, I want your trend line. I want the experimental acceleration due to gravity, 2 times the A coefficient. What about the initial velocity? If I look at my trend line and I look at my equation, I can see that the B, the coefficient on T or X, is identical to my V naught. Should my V naught be 0? Yes, I'm dropping it from rest. Will it be 0? No. Also, C, I didn't ask for it in the data or in the table of results. C is identical to your initial position. Should that be 0? Yes. But B and C won't be 0. And the reason why they won't be 0, I want you to put the coefficient B here. That's your initial velocity. And I want you to put the percent error. The reason why they're not, does anybody know? Does anyone want to turn on their microphone and tell me why the initial velocity and the initial position on the trend line won't be 0, even though they will be 0 on our experiment? It's a type of error. It's either standard or random. If it's random, over many, many trials, they should all average to 0. So what that means is it must be systematic error. If you have a B and C coefficient in this trend line, you have systematic error. That means you have something that is altering every single measurement you take. That could be air resistance. That could be that your ruler doesn't quite start at 0. It's a little bumpy at the bottom or whatever. It could be some other systematic error that you can think of. It could be a timing error in the electronics that you're using to time, whatever it is. But it's not random. It's the same for every measurement. That's what systematic error is. What's really nice, and this is really important for those of you who are going to go on to be scientists, knowing that that systematic error is there from the graph, you can go back and look at your experiment and figure out where it came from. Figure out what is off in your experiment that's giving you bad data. And this experiment really clearly shows in that B and C coefficient that you have systematic error. A little bit of random because we're only doing 3 trials at each distance. But if we did like 1,000 trials, that random error would all go away, because sometimes it would be a little plus, it would be a little negative. Random error in this could be that you're not exactly lining it up to 20 centimeters for all 3 of the 20 centimeter drops. You're a little high, you're right on it, you're a little low, but over enough measurements, that would all go away and it wouldn't affect your error. Obviously, we're only doing 3 because I don't want you to have to be there for 4 hours, you know. So our first set of questions here, and remember your questions need to be typed, double-spaced, complete sentences. The first is, which of these would you classify as systematic? Which would you classify as random? Number 1 is a trick question. Air resistance, I don't care if you call it random or systematic. You might decide that it's random because it is different depending on how you drop the coin and how the coin tumbles, and so it's a random error in your experiment. Someone else might say it's systematic. Air resistance is the same every time. I don't care as long as you justify why, give me a reason why. Attempting to drop the coin from the same exact position for all drops, that is definitely random. Sometimes you'll be high, sometimes you'll be low. The zero error of your meter stick means that when you measure 0, you're not truly measuring 0. There's a little bit more or a little bit less. So maybe the first line on your meter stick is actually like rubbed off. Mine's a little rubbed off. So the meter stick 0 means that your meter stick is not quite calibrated right, and you're always going to be off by whether it's too long or too short, right? So meter stick 0 are always systematic. It's the same for every measurement you make with that meter stick. So that's just making sure you guys understand random versus systematic errors. This second question says, is there any noticeable trend? I want you to look at these values and see, do they increase as they go up? Do they decrease as they go up? Are they just all over the place and they don't matter? Typically in this experiment, they're all over the place. They don't matter. You'll have like a 1% and then like a 5% and then a 0.5% and then a 0.7% and then like a 3%. They're going to change. And that's okay. Someone might get it where they're increasing or they're all 0 or whatever. Just tell me what you see in your percentages. Does the quadratic trend line accurately relate the distance? Now, if for A, for B, for C, they ever ask you, does your trend line accurately reflect your data? What they're asking you is R squared sufficiently close to 1? For this question, quote your R squared. Question 4, what is the physical significance of the y-intercept? I already told you, that is the initial position. We're assuming that the initial position is 0, and it won't be on your trend line. So do you categorize this as systematic or random? Well, if we did 1,000 experiments, it would be systematic. All the random error would cancel. However, we've only done 3, so there might be a little bit of random. Just to explain that again. This last part, we're going to ask you on almost every lab. Identify the independent and the dependent variables. Now, if you don't know what these are, independent and dependent, I really hate those names. What they should call them is independent variables are the variables that you decide on. So we choose the distances that we're dropping this coin. We can choose the mass of this coin, right? We can choose all sorts of things. Anything that we can vary, anything that we can change in the experiment is an independent. A dependent variable is anything that you are either measuring or calculating from your data. What are we measuring or calculating here? We are measuring the time it takes to fall, and we are calculating the value of G. Dependent variables are things you measure. Independent are things you vary or control. There's a third thing called fixed that we'll talk about another time, but fixed variables are variables you have no control over. That would be like gravity in the room. So just remember, independent is actually kind of a misnomer because I associate independent with things that you can't change. Independent means things that you can change as the experimenter. Dependent means things that you measure. And I'm sorry to go on and on about that, but we're going to ask you over and over again and make sure you really have those down in this class. All right, so last, you're going to get some value of G. Let's say you get, your slope is 4.78. So you multiply that by 2 and you get what, 9.56. And it's less than gravity. I want you in the conclusion. I want complete sentences. I want double-spaced. I want paragraphs. But what value did you get? Just quote me the value you got. Tell me the percent error between the theoretical and the experimental. Some of you, I'm going to grade your other 2 labs this weekend, probably tomorrow, but this weekend, that are turning in today and last week. But some of you didn't, on that very first graphing lab, give me numbers. Always numbers. Back everything up. Say the percent error was 4% or whatever it is. Give me the trend line. Give me the coefficients of the trend line and tell me that they mean the initial position, the initial velocity, the initial acceleration of gravity. Tell me what they are. Tell me what they mean. Are there any weird errors in your mean time uncertainties? So if you have anything in your data that looks weird, talk about it. Tell me why. Maybe you just did a bad job dropping the penny or timing it or whatever. That's cool. But make sure that you talk about any large weird errors in your data. Tell me how good you match your data. Quote your R-squared value. Tell me what values you expected the trend line to have and tell me why they're different. What I'm saying here is B coefficient should have been 0, C coefficient should have been 0, and they're not. They're different because you have error in there, and that's fine. Tell me what you think the main source of error is here, not human error. Don't tell me that. I mean, you can tell me human error like it was very difficult to exactly line the center of the coin up to 20 all 3 times, or it was difficult to exactly figure out how much time from the time you said drop to the time it hit the ground. That's fine. But I really want to hear things like error resistance, things like that. What you think was the main source of random error, and it's probably human. I know I say don't say human error. You can say human error in this one, but normally you don't ever blame yourself. You assume that you're doing a perfect job. This particular experiment, most of it is human error. And then lastly, how would you change the experiment to make it better or more interesting? Please do me a favor. Everyone always says we do it in a vacuum. Try to come up with something different. If you absolutely can't, if you want to be, give the lazy answer, we do it in a vacuum so there's no error resistance. What I want to know is a better way to do this experiment. In the lab, when you do this in person, it's really nice. They have the ball in this metal contraption, right? And it's completing a circuit. And once you break that thing loose, the timer starts. Once the circuit's broken and it falls, and when it hits the ground, it hits an impact sensor that stops the timer. So you get perfect timing. You don't have to do any of this like, oh, well, this is where I started to say drop and this is where it hit the ground, or how fast you have to do. It totally does it for you. So if you could come up with a way to time this, maybe do it on video with a timestamp where you can see right where you dropped it and right where it hit the ground, and you could exactly measure the time. The last thing, though, that I do want to bring up, that I forgot to bring up in 3, we're assuming that gravity is 9.8. What if you're living on top of like an iron deposit and gravity just happens to be like 9.9? Or what if you're in Albuquerque or Denver where you're a mile high up and gravity is a little bit less? Maybe the value of, if you get 9.7, maybe that's the actual value of gravity at your particular location. That could be 2. If you get like 9.1, chances are no, that's not true. But if you get like 9.78, you might have gotten the true value of gravity at your location. So just give me some good answers. I tried to give you lots of stuff to talk about. Essentially, in the conclusion, you present your results with numbers. You talk about the error and where you think it came from, and then you talk about how you fix it. So I gave you a bunch of stuff to talk about if you were a little lost on what to talk about. You don't have to talk about all of it. I really just want you to give a nice conclusion, and this is for people who need help with that, okay? So are there any questions on this? This lab is actually not too bad as long as whoever does the experimenting can figure out a good way to get their times, and that they make sure and get these delta T and delta D and delta T right. Everything else is pretty easy. I would have someone do the questions and conclusion, have someone do the calculations and the graph, and have someone do the data. Would probably, if there's 3 of you, no more than 3 of you though, please. Okay, any questions on that? If not, I want to go through the homework and then I want to get out of here. It's Thursday and I'm done for the week. All right, let me stop the thing.